Hello everyone. Today we are going to discuss about the Monte Carlo simulation technique that is being used extensively in structural reliability in order to calculate the reliability of a particular structural element of the structure as a whole. So this technique is basically a simulation technique where we can computationally calculate the reliability. So let's get into the thing of it. So we are going to discuss about Monte Carlo simulation. So mostly I'm going to follow the book of R. Ranganathan and his procedures, whatever is mentioned in the book, that is going to be explained to you in this video. So let us see about the failure of a flange. Under what conditions does the flange fail? So few conditions are: number one, suppose y1, the condition y1. The first condition may be if the section is under reinforced. So that is one, the section is under reinforced and the neutral axis lies in the flange. Okay. Another case might be if the section is under reinforced and the neutral axis lies in the web. Okay. So two conditions. Third one might be if the section, now we are going to go to the over reinforcement, is over reinforced. The section is over reinforced and the neutral axis lies in the flange. Next would be if the section is over reinforced and the neutral axis lies in the web. So I have here four criteria, y1, y2, y3 and y4, where I can see that the failure of my section might occur. So now if I have to write down mathematically how this failure of this section is going to occur. So I have here, so the probability of failure. The probability of failure of this section, what does it depend on? It depends on the probability of failure given that a particular event has already occurred, yi has already occurred, into the probability of yi. I'll just explain it a little bit how I got to this one. So I am here writing I equals to 1 to 4 because I have discussed here four different conditions, y1, y2, y3 and y4. These are the four different conditions that I have considered here. That's why I have I equals 1 to 4. Now, how am I going to find out the probability of failure? The probability of failure should be, first and foremost, one of the conditions have to occur. If one of the conditions has occurred, now let's go back to y1 a little bit. So y1 is if the section is under reinforced and the neutral axis lies in the flange. Okay. So let us assume that you have a section where it is under reinforced and the neutral axis also lies in the flange, but that does not guarantee that your section is going to fail. So there is a probability of failure. There will be a probability of failure when certain criteria are met. So this probability of failure, given that your event yi I, in this case what I have told you is y1. Given that y1 has already occurred, what is the probability of failure? This is denoted by PFYI, which is the conditional probability. Condition that yi has already occurred, what is going to be the failure of your section that yi has already occurred, multiplied by, sorry, I have given here double dot, you should understand this is a multiplication. A multiplication PYI, which means what is the probability that the event itself is going to happen. This probability that the event itself is going to occur multiplied by the probability of failure once the event occurs is going to be the probability of failure of that event, and you sum up on the number of events that you have. In this case I have y1, y2, y3 and y4, so I have 4 events. So if I sum them up, I'll get the probability of failure. In other words, I can also say that I equals 1 to 4 probability when r minus s is less than 0 and y1 has already occurred, or sorry, yi has already occurred, multiplied by pyi. Okay, so as we already know, r minus s, r is my resistance and s is going to be force. So whenever the probability that yi has already occurred, after yi has occurred, suppose already the section is under reinforced and the neutral axis is in the flange, so this one has already occurred, but that does not guarantee that there is going to be failure. What guarantees that there is going to be failure is when the force is going to be greater than the resistance of the section. So this is the probability of failure when yi has already occurred into the probability of yi. What is the probability that yi itself is going to occur? Okay, so now what we have here is what we have seen in previous units also, that my resistance r depends on many factors. So if it might be a function f or a function g, sometimes it is mentioned on x1, x2, x3, x4, dot 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 xn. Let me just not go ahead with all the indices, it's pointless. So x1, x2, x3, x4, xn, dot 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 xn. So where your xi's might be either your material properties, or they might be geometry properties. Okay, so that they might be material properties or they might be geometry properties. So material properties are what? Suppose the Young's modulus, the Poisson's ratio, and any other constants that define the material itself. Those are the material properties. Otherwise they might be geometry properties where the geometry of the section is considered. Let's say the breadth, the depth, the length of the section, and any other considerations that we have on the geometry. So these are the geometry properties, and this might be the material properties. So xi can be either material properties or they might be geometry properties. So that completely depends on how you are going to define the resistance of your section. So okay, so let me just change the page. So now I have seen that my resistance depends on many factors, x1, x2, dot 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 xn. So these parameters that I have, they are actually random parameters. They can be anything. They can range in values and have any values. So, but there might be constraints depending on the type of problem that I have. I cannot have, let's say, Young's modulus is infinity, or I cannot have the depth of the beam as, let's say, 1 kilometer. These are pointless things. So, but then there is a range of my parameters that I will have. But depending on that, even within that, suppose let's say that the depth of the beam can be from, let's say, from 300 meters to 500 meters. But it can be anything. It can be 301.1, it can be 305.6, 312.9, any random values within that range it can be. So basically what do I have here is my resistance equation. If I'm going to write it as a small r, the resistance equation that I have. So the resistance equation that I will have depends on my x, I have here small x's, small x1, let's say small x2 dot small xn. Okay, so my resistance equation is this: R equals x1 x2 x3 small xn. So these x1 x2 x3 xn are again my geometric or my material properties, but then these are going to change because these are random. So I might keep here, let's say x1 is the depth of the beam, so I might keep here 301, 310, 305, that depends on me. So that whichever I am keeping is my kth value. So this is kth value. Okay, so this is my kth value here. I think you can see it here. So this is my kth value. So this resistance is also my kth resistance. So my kth resistance depends on all these factors. How I'm going to vary all of these factors. These are the either material properties or the geometric properties. So this is going to give me the resistance Rk.